Hi everyone, my name is Aklant Kumar Bhowmick and I'm a postdoctoral research associate at the University of Florida Theoretical Astrophysics Group working with Laura Blecha, and prior to that I was a graduate student at Carnegie Mellon University where I worked with Tiziana Di Matteo, and I graduated with a PhD in the fall of 2019. And in this video, I'll be talking about some recent results, which I worked on very close collaboration with Laura Blecha and July Thomas on the impact of environment on supermassive black hole fueling and AGN activity in the IllustrisTNG universe. So the broad question that we try to answer with these kinds of works is essentially what is the key physics that drives AGN activity in galaxies. And there are two key requirements for any process to drive AGN activity. First is that we need a steady supply of cold gas, and second is that they need some mechanism for the gas to lose its angular momentum. There are two broad categories of processes that can satisfy these requirements. On one hand, one can have secular processes that occur within the galaxies, and these include processes such as stellar winds, gas accretion, and hydrodynamic instabilities of gas, such as the bar instability. On the other hand, one can also have external disturbances that the galaxies can be subjected to in the form of major mergers or interactions, and this is going to be the major focus of this particular talk. Galaxy mergers and interactions are very interesting because these are precursors to what would eventually form gravitationally bound black hole binaries, which are going to be sources of gravitational wave detections in future facilities such as LISA. And this offers a very exciting prospect in the light of the upcoming era of multi-messenger astronomy. So in terms of the role of galaxy mergers in driving AGN activity, there are two fundamental questions that need to be answered. The first is, does a connection between AGN and mergers exist in the universe? And if it does exist, what is its relative importance compared to secular processes in driving AGN activity? And furthermore, is there a dependence on luminosity redshift to the answers to these questions? So observationally, a vast majority of AGN hosts actually do not show any signatures of recent mergers in their morphology. Here's an example of a set of AGN hosts which were analyzed in some recent works, and you can see that if you look at the morphologies of these hosts, they do not have any disturbances that are typical of mergers or interactions. At the same time, galaxies that are indeed found to be merging or interacting, they do tend to have a higher fraction of AGN hosts compared to non-merging galaxies. Here are a few examples of such merging and interacting systems. And here is a result from Ellison et al. 2013, which looked at the AGN excess plotted in the y-axis, which quantifies the fraction of AGN fractions of merging or interacting galaxies divided by that of non-merging galaxies, plotted as a function of the projected separation here in the x-axis. And we see that at smaller projected separations, there's higher AGN excess, and this is a very convincing signature of a possibility of galaxy merger, or sorry, a merger AGN connection. And so overall, we see that with all these observational works, the overall evidence of the importance of merger AGN connection in driving AGN activity is still mixed, and further more work needs to be done to get a much more complete picture. So the question we ask in this work is whether we see enhanced AGN activity associated with galaxy mergers in cosmological hydrodynamic simulations, given all the physics that we put in these simulations. And we use the Illustris simulation to investigate this. IllustrisTNG is essentially a suite of simulations which runs all the way to zero using the ARIPO cosmological hydrodynamic code. And this contains a wide array of physics such as gravity, gas magnetohydrodynamics, star formation, black hole growth, and stellar and AGN feedback. So we essentially in this talk, we present the results from the TNG 100 box, which has a size of 100 megaparsecs per side and a few tens of million particles. And this volume and resolution allows us to reveal the overall large-scale structure, which is shown here in the form of the dark matter density field, while at the same time also resolving individual galaxies and black holes shown in these inset panels. So here in this work, we essentially exploit the fact that galaxy mergers would naturally and organically lead to the formation of black hole systems. So what we do is essentially identify these black hole systems in the simulation and analyze their AGN activity. So our methodology can be represented with the schematic over here, where we show where these black points correspond to a spatial distribution of a very small subset of black holes that can be found in the TNG 100 box. And we essentially link together these black holes using a maximum distance criterion, which is denoted by Dmax and shown by this horizontal line over here. And if we apply this particular criterion to this particular subset, for example, we end up with this particular black hole triple system being identified here, such that all these, each member of the system is linked to at least one other system within a separation distance of Dmax. One other black hole, within a separation distance of Dmax. So we applied this methodology and identify black hole systems at separation scales of 1 megaparsec, 0.1 megaparsecs, and 0.01 megaparsecs. And this range of separation scales is meant to encompass different stages of galaxies and halo mergers. For example, 1 megaparsecs corresponds to typical distances between black holes living in two different halos that have just merged or are very close to merging, but the galaxies are still far apart to be interacting yet. So here's an example of such a system where we see that the background panel shows the dark matter density field such that going from dark red to bright yellow shows increasing density field and increasing values of gas density, the black holes are represented by these green dots over here, and as you can see, they live in separate galaxies that are not yet interacting. And then we can also look at 0.1 megaparsecs, which corresponds to typical distances between black holes hosted by interacting galaxies. Here's an example image of one of these systems where we see a black hole hosted by a very bright central galaxy, and the other black holes in the system hosted by satellite galaxies, and the central galaxy is tidally stripping the satellite galaxies. And then we also look at 0.01 megaparsecs, which corresponds to typical distances between black holes hosted by merging galaxies. And here's an example of such a system where the galaxies have already merged, but the black holes are still in the process of undergoing a merger. One thing to note is that these separation scales that we consider here are significantly larger than what is typically associated with gravitationally bound black hole binaries. So it is essentially the limited resolution of the simulations that prohibits us to go further down these scales and trace later time evolutions of these systems, but there are post-processing models which are able to do that. And for people who are interested in this particular aspect, I urge you to refer to Muhammad Saeeb's work, who is also giving a presentation in this as part of the symposium. So now let's summarize the overall abundances of these black hole systems in the form of so-called black hole multiplicity functions, which is essentially the number of black hole systems as a function of black hole multiplicity, where the multiplicity is defined to be the number of black holes within a system. So a value of 1 represents a black hole single, 2 represents black hole a black hole binary, and a triple and the quadruple, and so on and so forth. So, and then these different panels from left to right corresponds to separation scales of 1 megaparsec, 0.1 megaparsecs, and 0.01 megaparsecs consistently for the next couple of slides in the simulation, in this talk. And if we look at the trend with respect to decreasing separation distances, we see that the number of rich black hole systems such as binaries, triples, and quadruples, and so on and so forth, they decrease with decreasing separation distance, which is what we would expect. And if we look at the overall numbers at different redshifts, for instance at redshift 0, represented by this blue line, we find about 3000 pairs, 700 triples, and 100 quadruples at scales of 1 megaparsecs. If we go down to scales of 0.1 megaparsecs, we have about 600 pairs, 100 triples, and 20 quadruples. And at 0.01 megaparsecs, we have about 60 pairs and no triples and quadruples at these scales. Now let's look at the overall AGN activity of these black hole systems. We first start with the AGN fractions, which is defined here in the y-axis as the fraction of black hole systems which have at least one active AGN above a specific choice of Eddington ratio threshold. Here we look at Eddington ratio thresholds greater than 0.7, so which corresponds to some of the highest Eddington ratios in the TNG 100 box. And if you look at these dashed lines over here, they essentially represent the AGN fractions of sets of randomly selected sets of black holes. And the fact that that increases with multiplicity is a simple reflection of combinatorics, where it essentially says that the larger number of larger sizes black holes, larger sets of black holes that we select, larger is the probability that we will end up with at least one active member. However, it gets interesting when we compare this trivial increase to that of the solid lines, which corresponds to AGN fractions of true black hole systems. And in particularly when we look at scales of 0.1 and 0.01 megaparsecs, these AGN fractions of these black hole systems are significantly enhanced compared to that of randomly selected sets of black holes, and these enhancements are up to factors of 3 to 6. However, when we look at separations of 1 megaparsec scales, we see no such enhancements. Conversely, we can also start with a sample of AGNs and ask the question of what fraction of AGNs, what fraction of these AGNs are associated with companions, and which is plotted here in the y-axis as a function of the threshold critical Eddington ratio. Again, the solid and dashed lines correspond to true black hole systems and sets of randomly selected black holes respectively. And if we compare the solid and the dashed lines, we see that at high enough Eddington ratios, particularly at 0.1 and 0.01 megaparsecs, these AGNs have enhanced likelihood of being associated with companions compared to what you would expect from a simple random selection. Moreover, we must also note that despite these enhancements, if you look at the overall fraction of AGNs that are associated with companions, it is only up to 40% at 0.1 megaparsecs, and naturally even smaller for 0.01 megaparsecs. And this implies that a significant majority of AGNs still are not associated with companions and are therefore likely driven by secular processes. The same enhancements, if we look for in 1 megaparsec scale separations, we see no such enhancements at these scales. So lastly, let's summarize the overall impact of these merger-driven enhancements on the Eddington ratios. So here we'll plot the median Eddington ratios of these black hole systems as a function of redshift on the x-axis, and these different colors of black, maroon, and violet corresponds to single black holes, black hole binaries, and black hole triples respectively. And if we focus again on length scales of 0.1 and 0.01 megaparsecs, we see that the median Eddington ratios of black hole pairs and black hole triples are enhanced by up to factors of 2 to 3 compared to that of random sets of black holes shown by the dashed lines. And we also, in addition, see that these enhancements are more prevalent at higher redshifts compared to lower redshifts. And this is a simple consequence of higher availability of gas to feed these mergers at higher redshifts. And lastly, again, at scales of 1 megaparsecs, we don't see any significant enhancements. So to summarize our results, we've investigated the AGN activity of black hole systems and find enhanced AGN activity in the form of enhanced AGN fractions by up to factors of 3 to 6 for the AGN at Eddington ratios of greater than 0.7 at scales of 0.1 and 0.01 megaparsecs. And then conversely, also we see that high Eddington ratio AGNs greater than 0.7 Eddington ratios also have an enhanced likelihood of having companions at 0.1 and 0.01 megaparsecs compared to what you would expect from a random selection. And then no such enhancements actually exist for systems at scales of 1 megaparsecs, which hints to us that these enhancements are likely driven by mergers and interactions. At the same time, while these enhancements do exist, only about 40% of AGNs have companions, but this implies that a significant majority of the rest of AGNs are likely driven by secular processes. Additionally, the merger-driven enhancement in Eddington ratios is at best up to factors of 2 to 3, and overall these imply that while merger-AGN connection exists, they play a relatively minor role in driving AGN activity. And we also note that there's exciting prospect of detecting these systems using current and upcoming X-ray facilities, and more details about this particular aspect can be found on the paper that I've linked at the very beginning of my talk. And And finally, like these systems can be used to constrain in spiral timescales and merger rates of massive black hole binaries in laser. Thank you so much for this opportunity, and I would be happy to answer any questions that you have.